Hello everyone, today I am presenting DICEPTION, a groundbreaking generates diffusion model for visual perceptual tasks. Let me start by explaining the problem this paper addresses. Current vision foundation models are excellent at single tasks, but they struggle when it comes to multitask realization. Training these models from scratch requires massive computational resources and enormous data sets. Additionally, task representations in CV differ substantially, making it extremely difficult to create a unified approach. And when researchers have tried building multitask models, they typically underperform compared to specialized single task models. So the authors asked an interesting question: can we leverage the powerful priors from pre-trained experiments with diffusion models to build a robust multitask perception model? Their hypothesis was that diffusion models, which have been trained on billions of images, contain rich visual priors that could efficiently transfer to multiple perception tasks. And as we will see, this intuition proved to be remarkably effective. And okay, so what exactly is that? That's it's a unified multitask perception model with fully shared parameters um, that can solve 6 different perception tasks, as you can see. What's remarkable is that it achieves performance comparable to specialized state-of-the-art models while using only 0.06% of SAM's training data. That's 6.6 million samples compared to SAM's 1 billion samples. On the right, you can see visual examples of dissection solving all these different tasks with a single unified model. Let's break down the task dissection handles. On the geometric side, it performs molecular depth estimation and surface normal prediction. For segmentation, it does interactive segmentation with point prompts, entity segmentation, and sense segmentation, and finally, it also handles human key point detection. This diverse task demonstrates the true generalist capability of the model. A key innovation in dissection is how it unifies all these different tasks into a single RGB representation space. A single channel outputs like depth maps or binary maps simply repeat the channel treatment. Three channel outputs split surface normals map directly to RGB. This elegant unification strategy allows the model to treat all tasks consistently. So here's our overall architecture of dissection. The pipeline shows how different tasks are unified through RGB encoding, processed through the diffusion model, and then decoded back to the respective outputs. Notice the point embedding processing for interactive segmentation task and a fully parameter sharing DIT architecture that processes all tasks to the same network. The architecture leverages token based pagination and flow matching, also enable efficient multitask learning. For interactive segmentation, dissection uses a clever point embedding approach. User provided points are encoded with some user position including and processed through a two-layer DSP. It uses learnable embeddings to distinguish between valid points and invalid points. During training, they randomly sample 1 to 5 points and fire the sequence to length profile, which makes the model robust to varying numbers of input points. So the training setup is remarkably efficient. They use approximately 1.8 million samples across all tasks and train for 24 days on just flow and video, 800 CPUs. For testing surface normal tasks, we use 0.5 million samples from open images, synthetic annotations. For interactive segmentation, they use 0.6 million samples from a single MB combined with mapping datasets. This is a fraction of what typical large-scale vision models require. Okay, let's look at the results, starting with depth estimation. Dissection achieves highly competitive performance with specialized data models. On KITTI, it uses an absolute relative error of 0.069 compared to depth flow 0.055 at metric 3Ds. V2s were 0.052. On NY-UV2, it reaches a delta 1 accuracy of 0.960, very close to depth, anything is 0.980. Importantly, it significantly outperforms the multitask baselines like Painter Unified IO 4 MXL. Okay, so the segmentation results are even more impressive. Here you can see that even into the point of view of the comparing dissection with SAM IITJ on surface and estimation task. What's remarkable is that dissection matches SAM's performance by using only 0.06% of training data. That's 0.6 million samples versus 1 billion. The bar chart on the right shows total MIOU comparison across different data sets, demonstrating that dissection achieves results on par with SAM despite the massive data efficiency advantage. One of the most exciting capabilities of dissection is rapid future adaptation to the entirely new tasks with just 50 training images and fine-tuning less than 1% of the total parameters using LORA with random with hit on attention layers. The model can adapt to novel tasks like multiple segmentation, including non-segmentation and image segmentation, as well as creative tasks like image highlight. This basically demonstrates exceptional transfer learning capability of dissection. Through comprehensive application studies, authors discovered several key differences. First, token-based concatenation is superior to channel-based concatenation um, for combining inputs. Second, the DIT architecture is better than network preserving pre-trained bias. Third, model um, third, best models classify free guidance with a scale of 2, improves depth and normal quality, and fourth, multi-step training and naturally enables few-step inference without additional manipulation. Um, okay, so basically, additional findings include the importance of pixel-aligned um, training, which significantly enhances detailed preservation in outputs. They also found that simple task problems like chemistry depth or initial normal are sufficient. You don't need a complex problem scenario. Preserving the pre-trained bias from the diffusion models, the paramount for success, and you don't need complex models or training techniques to achieve great results. Sorry. Okay, it's worth comparing dissection with one diffusion. Another recent diffusion-based vision model. One diffusion is simulation focused trained on 75 million samples from scratch. In contrast, dissection is perception focused using only 1.8 million samples while leveraging pre-trained models. As a result, dissection achieves higher quality and more stable perception results with a clear distinction between encoding measurement and distinct signals. Okay, to summarize the main contributions, dissection is the first unified multitask perception model that matches specialized data performance across multiple tasks. The paper provides a comprehensive analysis of design choices for diffusion-based perception. It demonstrates efficient use of blue-shot adaptation with minimal parameter update, and it shows that pixel-aligned training is crucial for enhancing detailed preservation. The advantages of dissection are substantial. First, there is massive data efficiency. Second, low computation cost. And third is quick adaptation requiring just 15 minutes and updating only 1% of the parameters for new tasks. Finally, the unified RGB prediction space enables matting level segmentation accuracy. Of course, no model is perfect, and the authors are transparent about limitations. The inference time is relatively slow. That's about zero point 0.8 seconds per minute on 800 GPU. Some tasks require post-processing steps, particularly key points and instance segmentation. Post-processing can introduce errors, especially for small objects, which leads to lower average precision scores on categories with many small instances. So preserving pre-trained priors is absolutely essential for success. Simpler approaches actually work better than complex architectures. Sometimes less is more. The flow matching enables flexible control over the number of inference steps and distributed broadcast training shows no performance gap into single task training, which contradicts some previous beliefs in the field. Okay, so looking ahead, there are several exciting directions for future work. First, scaling up with larger and higher quality data sets. Second, developing faster inference techniques using future computing methods. Third, exploring models' ability to compose multitasking with them. And fourth, improving post-processing pipelines to reduce metric degradation, particularly for small object detection. So, in conclusion, uh, Dissection demonstrates that leveraging diffusion models provides efficient and effective pathways to multitask visual perception with minimal data and computational resources. This work opens up new possibilities for building generalist vision models that can match specialist performance without the prohibitive costs typically associated with training the models from scratch. Okay, so thank you for your attention. Goodbye.